Exercise number 4 from the textbook asks us to estimate a volume using a somewhat crude Riemann sum. We want to find the volume of the solid that lies below the surface z equals 1 plus x squared plus 3y, and above the rectangle R, which is the Cartesian product of the intervals from 1 to 2 and from 0 to 3. We're told to use a Riemann sum with m equal to n equal to 2 and choose the sample points to be lower left corners. Part B will ask us to use the midpoint rule to do the same thing. So I've gone ahead and sketched a graph of the rectangle in the xy plane. Remember how Cartesian products work. The first set is the set of values for the first variable. The second set is the set of values for the second variable, and the product is a set of ordered pairs. So this R is a set of ordered pairs where x ranges from 1 to 2 and y ranges from 0 to 3. So we get x going from 1 to 2, y going from 0 to 3. That gives us this rectangle here. We are told to use a Riemann sum with m equal to n equal to 2. These m and n are the number of subdivisions in the x and y direction. And for most purposes in this section, we will usually take those to be equal anyway, unless we have a particular reason for dividing differently in different directions, but we have that option. These are equal to 2, meaning that we are splitting each interval in half in its direction. And that means we cut in half this way and cut in half that way, so we get 4 little sub-rectangles. We're also instructed to choose the sample points to be lower left corners. This means that for each subrectangle here, we're going to take the lower left corner as the representative point for that subrectangle. This is analogous to back in Calc 1 when you worked with Riemann sums for integrals at the beginning, and you would do something like, for instance, take a left endpoint approximation. Not getting too fancy, just taking the left end of each subinterval. Well, here we're just taking the lower left corner, just somewhat arbitrarily. So we need to do a couple of things to work this out. First, we need to find how big delta A is, each area unit. This delta A would be the area of one little sub-rectangle. We see that that is 1/2 of a unit wide and 3/2 of a unit tall. So delta A is equal to 3/4. Each of these little rectangles has an area of 3/4. We've located where the sample points are. So now we can find an approximation for the volume. Remember the structure of the Riemann sum, skipping a lot of the details. It is a double sum over all of the function values at x and y sample points, multiplied by the delta A's, those little individual area units. So in this case, going through each thing, we have our function value here. I wrote z. Let me just treat the z as being the name of a... No, don't want to do that. Let me come over here and say, let z equal... back this up. Z equal f of x and y. This is much easier if we actually have a function to refer to. And I don't have a function name. So we can evaluate our function now at each of these xy pairs in turn. So let's just, since our sample points were lower left, let's just start at the lower left rectangle here. We have this rectangle. Its sample point is the lower left. That has coordinates 1, 0. So we'd evaluate f at the points 1, 0. And we would multiply that by delta A, which of course is 3/4. I'll write that in the next step though. And then we want to add the function value at the next point. That is 1.50 multiplied by delta A. and then add our function at the next point. This is 1, 1.5. The order of the points doesn't matter, of course. You just want to be careful to get the right coordinates. And finally, we have a fourth sample point, the lower left corner of the last rectangle. That is 1.5, 1.5. Okay, so we have this expression here. Now, in the next step, I'm going to do two things. I will start evaluating these and also factor out all of these delta A's. Delta A is the same in each case. It's 3/4, so that can be moved to the end, right? So let's just start evaluating here. We have 1, 0. So that looks like we'll have 2. 1.50, 0. 1.5 squared is 2.25, plus 1 will give us a 3.25, if I'm doing that mental arithmetic correctly. We'll see at the end how this comes out. We have 1, 1.5. So 1 plus 1 is 2. 3 times 1.5 would be 4.5. So it looks like we have 6.5. And finally, we have the 1.5, 1.5. So we have, let's see, what do we have here? That was a 2.25, plus 1 is 3.25, plus 4.5 sounds like a 7.75. 7.5. And as I said, I factored out the delta A. Delta A is equal to 3/4. Let's write that as 0.75. And let me check to see if that looks good. Okay, just checking against my notes there. And at this point, we have a bunch of decimal values. I suppose I could work this out mentally, but that would be a bit of a pain and kind of a waste of time. Let's just skip ahead to the results given by a calculator. This comes out to be 14.625. Of course, we could have done all of these as fractions and given an exact value here. However, this is just an estimate of the volume, so writing an exact value as a perfect fraction might be a little bit of a strange thing to do, since it's just an approximation. Writing it as 14.625 is probably clearer than writing that as a pure fraction. But yes, so this is an approximation to what you would get if you imagine taking the given surface and graphing that surface in the XYZ space and only looking at the part of it that's above this rectangle. Then you would get the volume of what's between those. And I suppose I should mention, I just sort of dove into this, assuming a certain thing about the problem. It does say above this rectangle and below that surface. And in order for all of this to work, the surface has to be non-negative. Our values here have to be non-negative. So we should take a moment to make sure that we won't get negative numbers here. Our x values range from 1 to 2, so x squared will be positive. Y goes from 0 to 3, so the 3y will at least be non-negative. So we have a positive number plus a positive number plus a non-negative number. This will be a positive number. So above this rectangle, z is always positive. So we do, in fact, get this does, in fact, give us the volume when we do this computation. If a problem wanted to be tricky, they could talk about the rectangle such and such in the xy plane and ask you for the volume that is above that rectangle and below some surface. And like I said, if they wanted to be tricky, they could have that surface actually intersect the xy plane at some point. And then you would have to figure out, okay, well, which part of the surface is above the xy plane rather than below it. If you just directly went in without considering that, then you would have you'd have some problems because you'd be computing some negative volumes. But most of these questions aren't trying to trick you like that. But I would recommend still take a moment to make sure that everything is working correctly and that you expect those to work out fine. Like I said at the beginning, this is a somewhat crude Riemann sum because we're only using 2 subintervals in each direction. We have this curved surface, and we only have 4 chunks we're considering, and we're approximating it by these lower left endpoints. If we wanted to get a more precise approximation, there are 2 things that could be done. One of them is to increase the number of subintervals, and in fact, that's the more likely one to be more productive. If we make our subdivisions greater and greater, if we make them large enough, we expect our approximation to get very close indeed. So that's our best option. But that is also a lot more computation. This is a very simple function, but working it out by hand is cumbersome. This would be very easy to compute with a computer or calculator if we automate the process, but a more complicated function could be time-consuming even then and still only give you approximate values. Another thing we could do is try to choose points that are more representative, and that is what Part B is about. Part B asks us to use the midpoint rule to estimate the volume in Part A. So now, we still have the same delta A, but now our volume estimate will be based on, instead of taking lower left corners, we're taking the midpoint of each rectangle, right? So, okay. So we'd want to evaluate our function at this point now and have coordinates. Now this is 1.5, so this x value is 1.25. And the y value is half of 1.5, which is 0.75. This is taking up quite a bit of space. Let's try to make this a little bit more compact here. Let's see, then we would have 1.75 for this x value and 0.75 here, delta A, plus the function evaluated at, let's go back to the 1.25, and now we have, let's see, 0.75 plus 1.5 looks, I guess, 2.25. And finally, this upper right point right here would be at 1.75, 2.25. Okay. These will be much harder to compute mentally. I don't think that's a useful use of my time here, and I would just pad out the video length for you to watch me just sort of work through all of that. But again, we would probably want to factor out the delta A, so we only have to do one multiplication at the end. Evaluate the function at each of these 4 points. We'd add those up, multiply by the delta A of 0.75, and in the end we should get 23.4375. Okay. I recommend that you do make sure that you can work this out. Try this yourself. Make sure you get that same answer with the aid of a computer or calculator. Unless you're up to the challenge of, or not really challenge, it's not hard, but if you want a little bit of practice with arithmetic and want to do it by hand, feel free. It's entirely approachable. But you see that we get this different estimate, as opposed to, what did we get here? We had 14.625 here. Choosing midpoints instead of lower left-hand corners, we got 23.4375. Well, that is certainly different. Is it better? Just from the information we have, it's hard to tell. Your experience from Calc 1 and Calc 2 should indicate that we would expect midpoints to be a better sample point, more representative of the region, but that is, lacking any information about the function itself. Some functions might be particularly bad at the midpoints of a particular collection of intervals. So in order to be more confident, we would probably want to create further subdivisions, iterate on this to get more and more accurate estimates, and see if those appear to be converging to something. Now, of course, the limit of these Riemann sums as the number of subdivisions approaches infinity is the actual volume, and that double Riemann sum becomes a double integral, which much of this section is devoted to evaluating. In the next video, I will work out the double integral that corresponds to the calculation of this volume and find out that the precise value of this volume is actually 23.5. Again, see the next video for the details of that. And now we can see that, oh, actually, the midpoint estimate was much more accurate than using the lower left corners. Again, with the lower left corners, we got 14.625. With the midpoint, we got 23.4375, much closer to the 23.5. And basically the reason for that, if we look at the expression here, is that in the x direction, we have this x squared going on. So x is 0 along the y-axis, and as we move farther away from the y-axis, it increases. So x equals 1 here. X squared is also 1. When x is 2, x squared is 4. So there's quite a bit of space going on in there. But if you think about the shape of a parabola, it's certainly not a straight line, but from 1 to 2, a parabola is a lot closer to being straight than it is from 0 to 1, right? There's much more curve happening from 0 to 1 than there is from 1 to 2. In the y direction, we have going from 0 up to 9, 3 times 3, and that is linear. So it's definitely linear in the y direction. So these are increasing. As x increases and y increases, their function values are increasing. The lower left corners were giving us an underestimate. That 14 point whatever was a lower bound. We knew that the volume had to actually be more than that once we figure out that that the function is increasing in both of these directions. If we took upper right corners, the upper right corners, these 4 points, then we would get an upper bound, because that we would expect each of those to be the maximum value of the function within that particular subinterval. So we could look at those lower and upper bounds and see how far apart those were to figure things out. And again, if you wanted to subdivide these further, but you still keep lower left versus upper right, then you can see your lower and upper bounds moving closer together and get a bound on the thing. Again, I need to stress that's only because on these intervals, this function is strictly increasing in the x direction and strictly increasing in the y direction. It's not the case that these corners will always give you upper and lower bounds. It depends on what the function is doing. But we have that sort of thing. And again, for this sort of surface, it's kind of almost linear. There is a curve, like I said, in the x direction. It's part of a parabola, so it's not perfectly linear. If it were just a plane, then we would expect these midpoint approximations to give us the exact value of the volume. Because when you average out a linear function like that, the middle value should be the average value, and you should get the correct volume. Since it's slightly nonlinear, then we got a result that was not quite accurate, but still quite close. So that's nice. A function that varies more, that has more bend to it, we would expect the midpoint to be a little bit less accurate. But that's the general idea here of numerically approximating volumes, or anything else, right? Just like in Calc 1, we motivated the integral first by considering the area under a curve, so we thought of the function value as being a height of a curve, but we later saw plenty of other things that those functions could be. Right? If a function represents linear density, for instance, of a wire or a thin rod or something like that, then integrating will give you the total mass of an object. Similarly, if this is a two-dimensional sheet here, and the function gives the density per unit area, then what we just did would be an estimate for the total mass rather than a volume. It all depends on how we're interpreting these things. But here we had z, which is a position, a height above the xy plane. So thinking of the function as giving us a height, we have a height times the area of the base giving us a volume there are plenty of ways of interpreting these things.